Good afternoon, good people. I don't have much in the way of new material to cover today. We have pretty much covered the core of it, but I do want to give us more practice with related rates problems. So today we can work on whatever you guys would like to work on. As far as material from this week is concerned. So we can look at some implicit or logarithmic differentiation stuff, just purely on its own, or we can look at some related rates. Or if you're feeling 100% comfy with all of that stuff, then we could reach forwards a little bit and sort of prepare you for what we'll be doing next week, which is where we'll be introducing some linear approximation techniques and min-max problems, along with a few other little things. So I am curious, how are you guys feeling about the material? What would you like to do today? Here's the syllabus. So reminder, we are here. We just finished the section on related rates. So we're a little bit behind the linear approximation and min-max problems. These sections will go fairly quickly. And then the graphing, curve sketching stuff, that is going to be a little bit tricky. So if we wanted to get a head start on the curve sketching.
Yeah, if you want to take it, you want to take it?
So how are you guys feeling about the implicit differentiation, log derivatives, and related rates stuff? Are there any problems there from the logarithmic differentiation or related rates homework that you guys would like to take a look at today? Okay, I'm not sure if you guys have gotten started on the related rates problems in the homework. I do want to warn that this is one of the sections that people tend to have a little bit of trouble with. I'm not seeing anything in chat or hearing anything from anybody. Okay, yeah, this, I have a feeling what Daniel says is a common theme. I have a feeling based on the silence that maybe many of us haven't started that homework. Yeah, okay, so while this is maybe understandable, it's not necessarily wise. So yeah, let's look at one or two problems from this week's homework. And then I'm going to start introducing the material from next week. Now, next week is going to be a little bit different because I'm going out of town Tuesday through Saturday. So I'll be pre-recording Wednesday and Friday's lectures. Yes, this week's homework is due Monday. So next Monday is going to be a normal class day for us. Homework 7 is due on that day, just like normal. So you do want to get moving on this. So let me grab for you one or two problems here to take a look at. There's logarithmic differentiation, differentiate the functions. So the study guide, let me see, we have a few sections to cover before the exam. The study guide I'll release once we're ready for the test. That will be when we complete section 4.7 on applied optimization. This will probably be next week. So right now we've finished up with related rates. The linear approximation section is very short. Then min-max, graphs of f and f prime, L'Hopital's rule curve section. I think we'll get through all of that next week. So maybe next Monday I'll be releasing the study guide. Probably Friday we'll finish the curve sketching, and then next Monday we will finish the applied optimization. So you can count on exam 2 probably being not next Monday, but the Monday after, the 26th, which puts us just almost exactly a week behind, which is okay. That's about where we figured we would be. Yeah. So let's come back here and start on notes proper for the day. This is MAC2311, section 4. It is a lecture day. And this is the 16th. Some kind of announcement. Exam 2, we can schedule is most likely going to be Monday, 10/26. Oh, let me zoom this way out. Okay. Monday, 10/26. So it's a week from next Monday. Yeah. So next week, we're going to cover the min-max problems, curve sketching, L'Hopital's rule, a little bit of linear approximation. And then the following Monday, we will discuss the section on applied optimization. And then that Wednesday, we might develop a little bit more material. Friday, we'll do a review for the test. And the following Monday, we will have the exam. Oh wait, 10/26, that might be, sorry, let me make sure I'm saying this right. So we are here. So next week will be 4.3, 4.4, 4.5. Next Monday, sorry, so not the exam going to be on the 26th. I'll release the study guide on the 26th. Sorry. Exam 2 will be then the following Monday, 11/2. And study guide 2 will be released. Yeah, sorry about that. Study guide 2 will be released Monday, 10/26. No, what this means is that we're not going to have exam 2 done before the drop date. Usually my goal is to get exam 2 done before the drop date, but that is not going to happen this semester, which is okay. But it does mean that you want to be thinking long and hard about how you're doing with the material. You want to be very, very honest with yourself, because the last day to withdraw is 10/31, Halloween, which will be before you get your second exam back, right? It'll be before the day of the test even. The study guide will be out. So what I would advise you guys to do is to treat study guide 2 like the test. Yeah, go through and time yourself on study guide 2, see how you're feeling, compare that to your result on exam 1, your homework scores and such. And you'll need to make a decision as to whether or not you want to stay in the class by Halloween. Okay, so all this said, let's look at a problem or two. All right, so here's our first example problem for the day. We want to find the derivative of this function. And it's a product of 3 pieces. Each of those pieces would require using the chain rule and the power rule. And you could jump in using the product rule on this. That's an option. If, however, I were to toss in something like this, now you would need a very complicated product rule to differentiate the top, power rule for differentiating the bottom, and to put it all together, you would need the quotient rule, which is nasty. So instead, what should we do? How do you differentiate a big, nasty thing like this if you don't want to use the quotient rule?
Put
If you
square
want
root
to
of
avoid-
x to -1.
If you want to avoid any mess of product rule and quotient rule, you do what? Daniel, I'm sorry, my volume was low.
Radical x to the -1. Or we could do the formula you gave us the other day.
So it's true that we can use the product rule in combination with the chain rule here, but there's an even slicker move. Yeah, we can differentiate logarithmically. And this will get us out of using even the product rule. We don't need any of that stuff. So we take the natural log on both sides. And we expand this out as much as we can using rules for logs. So this would first be the log of the top. And then you can expand the log of the top. Minus the log of the bottom. And we can go a step further, bringing the powers down. Like this. And by first expanding everything using these log properties, we turn all of the multiplication and division into addition and subtraction, and all of the powers into constant multiples. This makes the differentiation step itself much, much nicer. So now I differentiate on both sides with respect to x. My left-hand side here, remember, is the natural log of y. So when I differentiate this with respect to x, what do I get?
Y derivative over y.
Yeah, y prime over y. Right? The derivative of the outer function, the natural log, is 1 over y, and then you multiply by y prime. So that's 1 over y times y prime, or y prime over y. And on the right-hand side, when I differentiate each of these pieces, they're very, very nice. This is going to be 7 times the derivative of the natural log of 3x plus 4. So the 3x plus 4 goes downstairs, and then the derivative of 3x plus 4, which is 3, goes upstairs. Plus 5 times the derivative of the natural log of x minus 1. So the x minus 1 goes downstairs, and the derivative of x minus 1, which is 1, goes upstairs. Plus 13 times the derivative of ln 6 minus x. Well, that's 6 minus x downstairs, and the derivative of 6 minus x, which is negative 1, upstairs. And then finally, I have minus 1/2 times the derivative of ln x. That's just 1 over x. So then I can multiply by y on both sides to get y primed alone on the left. And this is going to be y times, and now I'll do what I can here. 7 times 3 is 21 over 3x plus 4 plus 5 over x minus 1 minus 13 over 6 minus x minus 1 over 2x. And then my last step, if I want an explicit formula, is to replace this y by what it is. Well, I know that y is this big gnarly fraction up here. So this y in my formula can be replaced by that big gnarly fraction, and then I get my nice formula for y prime. Y prime is 3x plus 4 to the 7 times x minus 1 to the 5 times 6 minus x to the 13 all over the square root of x times this expression, 21 over 3x plus 4 plus 5 over x minus 1 minus 13 over 6 minus x minus 1 over 2x. So that is by far the easiest way to differentiate this function. You take the natural log, expand everything out, differentiate implicitly on both sides, then solve for y prime. Okay, the advantage here is that each little piece that you have to differentiate is very simple. You are using the chain rule when we differentiate this to 3 over 3x plus 4 and all of these other logs. But they're very little chain rules, baby chain rules. So by using the algebra properties of the log, you're able to get rid of all the nasty multiplication and division that would call for the quotient rule and the product rule. Right? Zero product rule used here, zero quotient rule used here, only a little bit of chain rule. Much, much nicer.
Sorry, how are the chain rule turning into fractions when it's y prime over y?
Well, you have to remember the derivative of the natural log. So what's the derivative of ln x?
Oh, it's 1 over x.
Right. So if I have a composite function like ln of u, that would be 1 over u times u primed, which is u primed over u. So anytime I have to differentiate a natural log, I just get the derivative of the inside divided by the inside. For example, if I wanted to differentiate the natural log of sine of x, this would be the derivative of sine, which is cosine, over sine. All right.
Got it.
So the way I remembered that when I was in Calc 1 was stuff primed over stuff. The derivative of the natural log of some stuff is always that stuff primed over that stuff, or u prime over u. All right. So logarithmic differentiation is your friend. It's a nice, nice rule. Will help you differentiate big nasty products without using the product rule, big nasty quotients without using the quotient rule. And for certain things, like if I asked you to differentiate the function x raised to the square root of x, logarithmic differentiation is the only possible way because the base isn't constant, so this isn't a normal exponential function. The power isn't constant, so this isn't a normal power function. So the rules for exponentials and power functions don't apply here. But if you take the natural log on both sides, you can clean this up. x raised to the square root of x. Oh, well, this is a power inside my natural log. Remember, powers can come down. So this is square root of x times ln x. And now we can differentiate on both sides. So on the left, you get y prime over y. And on the right, when I differentiate this, I do need a product rule now. This would be the derivative of root x times ln x plus root x times the derivative of ln x, which is 1/2 x to the negative 1/2 times ln x plus root x times 1 over x. Now, this could be simplified a little bit, but if all you're after is a formula for y prime, then it's going to be y times this stuff. 1/2 times x to the negative 1/2 is 1 over 2 square roots of x. So you get that times ln x plus here, this is root x over x, which is 1 over root x. The simplification there, each piece is kind of off to the side here. 1/2 x to the negative 1/2 is 1/2 times 1 over x to the 1/2, which is 1/2 times 1 over root x. So that's your 1 over 2 root x here. And then the other piece, the root x over x piece, that's x to the 1/2 divided by x to the 1, which is x to the 1/2 minus 1, which is x to the negative 1/2, which is 1 over x to the 1/2. And then our last step here would be to replace y by what it is. Let's move that there. There we go. So what was y? It's x to the root x. So you have x root x times 1 over 2 root x ln x plus 1 over root x. So that's 2 logarithmic differentiation examples. The first one, you didn't need logarithmic differentiation. You could have jumped in using the product and quotient and chain rules. But by differentiating logarithmically, you save a lot of time and effort, and you solve an easier problem, meaning you're less likely to make mistakes. The second example, the one we just did here, you didn't have a choice. You had to use logarithmic differentiation because there's no rule that applies to functions like this, where the base and variable, or base and exponent are both variable. Any questions on this fellow?
In the exam, are you gonna tell us we can only differentiate using natural log?
There may be problems that say differentiate the following thing logarithmically, and there may be problems that just say differentiate this function, where you would have a choice. So on the one hand, yes, I could force you to use logarithmic differentiation in a situation where you're capable of using both. Or I could give you a problem like this, and you would have to recognize that logarithmic differentiation is the only possible way to go. So you're responsible for knowing when you need logarithmic differentiation. And then you're also responsible for recognizing when it will save you time. So if I gave you that first problem, just differentiate this thing, you could jump in if I don't tell you to use logarithmic differentiation and use whatever you wanted. But if you didn't use logarithmic differentiation, you might burn 20 minutes on that problem, which should really just be like a 5-minute problem if you do it correctly. So there's kind of 2 levels to this. If I don't specify a method, you are free to use whatever you want. But if you select the method unwisely, you may end up spending a lot more time on a problem than you want to. Does that make sense?
Yeah, of course.
Good, good. Good observation, Kyle. Yeah, we could put the natural log upstairs here, right? We could have called this ln x over 2 root x. That would be fine also. Yeah, in fact, we could put these together. Wouldn't be hard to have a common denominator there either. I just wanted to do a single thing in that step, and that was to replace this y by x to the root x. But what you said is exactly fine. You could have done that as well. It's a good observation. Any other observations or questions, comments? Okay. A quick show of hands. You can use the thumbs up react. How many want to be an engineer? How many's goal is to go into some sort of engineering? Okay. Yeah, so I've got some responses in chat and some in the reacts, some unsure. I think many people who take calculus will end up doing some flavor of engineering, whether it's called by that name or not. When you're looking to find applications of calculus, related rates is the core of that. There's another kind of thing at the center of it. Engineers love approximations, right? I once, when I was in grad school, spent no less than a year arguing with this asshole who happened to have been a tenured faculty member there, that engineers never need more than like 2 or 3 digits of pi. 3.14 is fine for everything, he says. And I say, no, that's bullshit. You're out of your mind. Like, the point being, he, in essence, was correct. Although I disagree that, that you would never need more precision. In many cases, good enough is good enough. And the perfect is the enemy of the good, meaning if the solution to some problem is some wild, irrational number, oftentimes we're happy if we can just get the first few decimal places. That'll be good enough to get done whatever it is you're trying to do. This is where the concept of linear approximation is going to come into the class. So before I go deeper there, let's do one related rates problem from the homework, and then I'm going to introduce this concept of linear approximation, with which we'll be working next week. So we did some logarithmic differentiation. Question 18 there is a lot of fun. 19 we did last time. 20 is a special application of 19. Cylindrical tank, radius of a sphere, plane flying horizontally. Let's do something that has to do with some trig. All right, so this problem is closely related to the airplane problem. This will be a related rates problem. It's not very popular in the United States, but have you guys ever watched Formula One racing? So the cameramen always impress the hell out of me at these F1 races because they've got a camera over here. And these cars are going by at incredible speed. And the cameraman has to pan the camera to keep the car in focus as it goes by. All right, so maybe right now he's looking this way, but he's going to have to rotate as the car goes by in order to keep the car in focus. Let's say the camera is 10 feet back from the center of the track, and the car is going this way at 100 miles per hour. So here's the setup for the problem. The camera is 10 feet from a racetrack, and the race car is driving past at 100 miles per hour. How fast does the cameraman have to, the term here is pan, like rotate from side to side, that's called panning the camera, to keep the car in focus, or in frame, I should say, at the moment when the car is right in front of him. So if you've ever done this sort of thing, tried to track a moving object by rotating a camera, you notice that when the car is way back here, you have to rotate much more slowly. And then as the car gets close to in front of you, you have to rotate much more quickly. And then as it goes away, you rotate more slowly again. There's a few reasons for this, but mostly it's to do with how far you are from the track and the overall distance from you and the object that's moving by. So the car is going at a constant speed. Let's say it's at 100 miles an hour. They're flat out. This is like a long straight. The car's top speed is 100 miles an hour, just to simplify things. In the moment when the car is right here, how fast is the camera rotating in order to keep the car in frame? That's the question. Is that clear? So when the car is way over here, you're rotating kind of slow, and then the car goes, meow, and then you can rotate kind of slow again to keep it in frame there. What sort of units is the answer going to have here? What am I looking for?
Feet per second.
Well, the camera's not moving along a line, is it? It's rotating. So this motion isn't like a forward and back or left and right motion. Yeah, Lucas got it exactly. Angular velocity. It's how fast am I rotating? So how many radians, you could say, per hour or per minute. So what we're looking for, what we want, I'm going to redraw this picture, taking out some of the complicated things. So here's the car. Here's the camera.
And we don't need to know the angle where we start at.
Nope. This angle right here, I can call theta. Then the thing I'm looking for, I want d theta dt. Or if you prefer the dot notation, remember the dot notation we introduced last time? I'm looking for theta dot. I know that this distance right here is 10. I can call this distance, the car's position, I can call that x. And let's measure that from like here, we'll do it like this. Let's measure that from like here to here. Okay. So I'll say this is the positive X direction. Over here, the car is at like -10, -50, because it's 50 feet to the left of that. Over here, the car would be at like +10 or +50. And the moment I'm interested in is where X is equal to 0. So in other words, X is the horizontal distance in this picture from the straight line to the car's position. Everybody understanding what we're doing? So you can think of it as a particle moving along the x-axis. And I've got my camera down here at like the point 0, -10. And I want to know what is d theta dt, the angular velocity, how fast theta is changing at the moment when the car zooms by here. So I'm going to need to set up some sort of algebra relationship, some sort of equation telling me how x and theta are related to one another. What do you guys see when you look at this picture that you could use to relate x and theta?
It's a right triangle.
Good. Now, more specifically, what is the relationship between x and theta?
We use cosine.
I wouldn't use cosine because this distance here, the hypotenuse of my triangle, is changing all the time. But this,
I meant tangent.
yeah, the tangent or cotangent would be fine. So the tangent of theta, I would use tangent, that's nicer, is the opposite over the adjacent. So if theta is down here, that's x over 10. Everybody see that? So now I want to differentiate through this with respect to t. So I'll take d dt on both sides. That's d dt of tan theta equals d dt of x over 10. First, are we all comfortable with where this came from? So if this is theta, this is a right angle, so I've got a right triangle here. Then the tangent of theta is always the opposite over the adjacent. So tan theta is x over 10. Now if I differentiate through that, d dt of tan theta is secant squared theta times d theta dt. And on the right-hand side, what is d dt of x over 10? Do I need the quotient rule there, or is there some other way to calculate that?
You could bring the x down.
Yeah, this is the same as d dt of 1/10 x, and the 1/10 is a constant. So there's no need to use any sort of quotient rule. The constant multiple 1/10 will pop out, and then d dt of x is dx dt. Nifty, right? If you wanted to use the quotient rule, you could. It's just going to be kind of sloppy looking. And of course, it would take longer. So now I'm at that phase where I want to ask, what do I want and what do I know? I know I want d theta dt. What do I know? Do I know what dx dt is?
100 miles per hour.
Good. Because the race car is going this way at 100 miles per hour. That's my increasing x direction. And at the moment where theta is 0, I'm sorry, I gave it away. At the moment when the car is in front of us, theta is 0, right? When the car is right here, this line is pointing right here. So we can plug these things in. Secant squared of 0 times d theta dt is 1/10 times dx dt, which is 100. What is secant squared of 0? What is secant of 0?
One.
Yeah, cosine of 0 is 1. So secant of 0 is 1 over the cosine of 0. That's 1 over 1. So secant squared of 0 is the square of 1 over 1, which is 1. So this piece is, if you want to write it, it's 1 over 1 squared, but times d theta dt equals 1/10 times 100 is 10. 1 squared is 1, so this is just the same as saying d theta dt equals 10. What are the units here?
Feet per second squared.
Not quite. So this is
Radians over seconds.
radians, so it's definitely radians over time, right? Rad per, but what am I measuring time in? What were the units of dx dt?
Miles per hour.
Yeah, miles per hour. So this is actually radians per hour. Cool, right? So there is a problem like this in your homework. Problem, oh, where did it go? Yeah, I hate that that doesn't show up in my alt tab stuff. The airplane flying over the radar station problem is very, very similar to this one. Oh, let's calc 2. I think it was number 26. Yeah, 24, sorry. Very, very similar. All right. So we've gotten a little bit more practice with logarithmic differentiation. We've gotten a little bit more practice with related rates. I'd like to take the last few minutes of class here, and I think we've got about 15 minutes to try and introduce to you the concept of linear approximation. how many of you have heard of general relativity? Probably most of us, right? I've at least heard the term general relativity. General relativity revolves around something called differential geometry. Differential geometry is kind of the idea of how do you do calculus in higher dimensional spaces? How do you do calculus on manifolds? You may have heard that space-time is a 4-dimensional manifold through which we move. The differential geometry perspective of the derivative is the best linear function to approximate any given function at a point. So here's an idea. The derivative of f of x at x equals a tells us the best linear approximation to f of x at or near x equals a. So let's say a is here. And this is the function f of x. Here's the point a comma f of a on the graph of f of x. Suppose there's some nearby point here. We'll call this nearby point x comma f of x. If it's very, very hard for me to figure out the y value here, then an alternate approach would be to look at the tangent line to f of x at a and try to find the y value on the tangent line instead. So the y value on the tangent line is very, very close to the y value on the graph of f of x. All right, here's the y value on the graph of f of x. You agree that those are close, right? And the line that does the best job of staying close to the graph is the tangent line, because it's got the right slope. If this line had any other slope, then these gaps between the line and the actual function would be larger. So this tangent line is the best linear approximation to the function f of x near x equals a. That's the idea. So if it's very, very hard to calculate this y value, the y value that's actually on the graph, then instead you should find the equation of the tangent line and plug x into it. What's the equation of that tangent line? It goes through the point a comma f of a, and the slope is always f primed of a. So if you use your point slope formula, that's y minus f of a equals m, which is f primed of a, times x minus a. We can solve this for y, and you get y equals f of a plus f primed of a times x minus a. Next semester in Calc 2, there will be a moment when I ask you, does this look familiar? These are the first two terms of the power series expansion for the function f of x about x equals a. Now, if you've never heard of power series, don't stress, that's a semester away. But this is the best linear approximation for the function f of x near a. We call this thing the linearization of f of x at x equals a. And it has a special notation. It's this big L of x equals f of a plus f primed of a times x minus a. And the neat truth is, if x is close to a, then f of x is very close to L of x. Yep, yeah, Calc 2 is my constant. I always do a Calc 2. They spin me around through other classes, but every semester I demand a Calc 2. By far my favorite class to teach. So, this thing, the linearization, is just the equation of the tangent line solved for y. If you ever panic and you're like, fuck, I don't know what the linearization is, this thing's asking me to use a linearization, just remember, oh, it's the tangent line. Just find the tangent line. The magic is, because the tangent line stays close to the graph, the y values on the tangent line are very, very close to the y values on the graph. And oftentimes in applications, specifically in engineering, but elsewhere, it's hard to calculate the y value on the graph. Like I know what the sine of 0 is, but I don't know what the sine of 0.1 is. So if I needed to find the sine of 0.1, rather than trying to plug that into the sine function, good luck, 0.1 sure as shit isn't on your unit circle, I would form the linearization for the sine function at x equals 0, and then plug in 0.1 for x. That's not the example I'm going to do here today. If there's time, I will do a slightly different one. Yeah, and there certainly is time. First, questions on the picture here, what we're saying. All right. So you may have heard that the square root of 2 is an irrational number. Which means it's hard to calculate. Now 9/4 is a perfect square. It's easy to take the square root of 9/4. And 9/4 is also pretty close to 2, right? 8/4 is exactly 2. So the picture here I'll try to draw it very carefully. Here's the graph of the square root of x. Nine-fourths, a little bit bigger than 2. So here's 1, here's 2. Right here is 9/4. And up here on the graph of the square root of x, here's the point 9/4, comma, the square root of 9/4, which is 3/2. What I would really like is the y value here. This point is 2 comma the square root of 2. And I want to approximate the y value, which is root 2. So what I'm going to do is find the linearization i.e. the tangent line which is the blue line and plug 2 in here. So this is 2 comma L of 2, where L of x is the linearization. And I think probably everyone would agree that just from the picture, we can see that L of 2 is very, very close to the square root of 2, because the blue point here and the red point here are very, very close in height. So I calculate the linearization of this function at x equals 2. Or sorry, at x equals 9/4 here. Of f of x equals the square root of x at x equals 9/4. Then plug x equals 2 into that. All right, let's do it. The linearization is the same as the tangent line. So I just need to find the tangent line. To do that, I take the derivative. F primed of x here is x to the 1/2 primed, which is 1/2 times x to the negative 1/2, or 1/2 times the square root of x. So f primed of 9/4 is 1 over 2 times the square root of 9/4. That's 1 over 2 times, well, the square root of 9 is 3. The square root of 4 is 2. And 2 times 3/2 down here in this denominator, those cancel, and we get just 1 over 3. So the slope of that blue line is 1/3. This tells me that L of x, which is f of a, f of 9/4, plus f primed of 9/4 times x minus 9/4. F of 9/4 is the square root of 9/4 is 3/2, plus f primed of 9/4, we just figured out that's 1/3, times x minus 9/4. This is L of x. And I know that L of 2 is very, very close to f of 2. The thing I want to approximate, the square root of 2, is f of 2. And f of 2 should be approximately the same as L of 2. L of 2 is what I get by plugging x equals 2 into L of x. So that's 3/2 plus 1/3 times 2 minus 9/4. I can clean this up. Two is 8/4, so this is 3/2 plus 1/3 times 8/4 minus 9/4 is negative 1/4. So that's 3/2 minus 1/12. And if you want to put that into a single fraction, you can. 3 over 2 multiplied by 6 over 6, that's 18/12. 18/12 minus 1/12 is 17 over 12. So the square root of 2 is very, very close to 17/12. It's not equal to 17/12. There is a tiny gap between the blue point and the red point, but it's tiny. So these guys are very, very close. You want to see how close? I'll give a minute for anybody who's writing, and then we're going to whip out a calculator. Let's do it. All right, first, square root 2. This is an approximation. It's a decimal approximation, and it's very, very good, right? The calculator is using something pretty cool here to do this. 17 over 12. Not too fucking shabby. First 3 decimal places are exactly correct. Square root of 2, 1.4142, blah, blah, blah. 17/12, 1.4166666666. So you get the first 3 decimal places of root 2 correct. And in the next decimal place, you're only off by a little less than 2 1,000ths. So here you're off by less than 2 over 1,000. That's 1 over 500. What is that as a percentage? You're off by less than 0.2%. Pretty good approximation right there. The calculator is actually doing something very, very similar to this when it approximates the root 2, when it gives you that decimal. It's just using a few more terms of the power series, and I'll be able to teach you all about that in Calc 2. So this is linear approximation. This is the whole section. The challenges here are really just in understanding the picture to see how this stuff works together. In practice, I'll give you the point that you're going to use as your base, and I'll give you the function that you're going to use to approximate. So a problem would be phrased almost exactly like this. Approximate root 2 using the linearization of the square root function at this nearby value.
So L of X is the tangent line at 9/4 comma square root 9/4.
Right.
And how do we know it's square root 9/4? Oh, we just plug into the function.
Yeah, because the function is square root x.
Yeah, 5 of X.
So L of x is just the tangent line at the specified base point. And then the idea is I can approximate the y values on the curve by using the y values on the tangent line instead. The magic here is that sometimes those functions, the original functions, are hard to plug into, but it's never hard to plug into a linear function. You'll only ever need to like subtract and multiply. No bizarre operations like take the sine of or take the square root of. So plugging into linear functions is always easy. Plugging into nonlinear functions, we know, can be challenging. Like, what the fuck is the sine of 1/3? I have no idea. But I could build a linearization to the sine function at some nice point near 1/3, and then approximate the sine of 1/3 using that linearization. The other stuff that we're going to be doing next week is talking about finding minima and maxima. I don't think you'll have a hard time with that because it's just the same as finding horizontal tangent lines. You've seen that nice smooth functions have mins and maxes at places where their tangent lines are horizontal. So that's quite easy. And then the remaining topics before exam 1 are applied optimization, where you take a real world problem and find a min or a max, and then sketching a graph of a function using information from its first 2 derivatives. So you use the first derivative to find where your function is increasing and decreasing. You use the second derivative to find where it's concave up, like bowl-shaped, or concave down. And with that information, you can actually sketch a very nice graph of a function, even if you don't know anything else about it. That section, section 4.5, is probably the one that is most challenging, which we haven't covered. So please work hard on these related rates and logarithmic differentiation problems, especially the related rate stuff. That's where people tend to get into a bit of trouble. And then next week, pay careful attention to the curve sketching, right? After that, we will have to talk about applied optimization, but I don't think you'll have too much trouble with that. And then we'll be ready for the test. So I'll be sending out the study guide Monday after next. And then the test will be a week after that. Between those, we'll have a few classes, one of which will be a review, but the other one will be us starting to talk about new stuff, stuff that'll happen after exam 2. Any questions for me before we wrap up for today?
Office hours today are normal?
Yep. Yeah, I will have an office hour from 2 to 3. Anything else? All right, then I don't want to push ahead too much further. We're already a little bit past what we were intended to cover this week. So I'm going to end it here. If you want to talk problems or anything like that, come see me in office hours. That'll be starting in just a little bit. Otherwise, I will see you guys on Monday of next week. Monday next week, normal class, right? Show up at the normal time. But then remember, Wednesday and Friday next week, I'll be out of town. So those will be pre-recorded lectures. You can watch them whenever you want. But make sure you come to regular class on Monday, okay? All right, take care, guys. Have a good day.